The story of the cosmic microwave background begins not with grand telescopes pointed at distant galaxies, but with two engineers in New Jersey working on a rather mundane problem in the spring of 1964. Arno Penzias and Robert Wilson were tasked with calibrating a horn antenna at Bell Telephone Laboratories in Holmdel, New Jersey. This peculiar-looking instrument, resembling a giant ear trumpet 20 feet long, had been built for early satellite communication experiments. Now repurposed for radio astronomy, it would become the instrument that accidentally discovered the echo of creation itself. As spring gave way to summer that year, Penzias and Wilson encountered a persistent problem. No matter where they pointed their antenna, no matter what time of day or night they observed, they detected a faint but steady hiss of radio noise. This wasn't the dramatic crackling of terrestrial interference or the rhythmic pulses of distant pulsars. Instead, it was a gentle, unchanging whisper that seemed to come from everywhere and nowhere all at once. The temperature of this mysterious signal measured about 3.5 degrees above absolute zero on the Kelvin scale. Such precision might seem unremarkable today, but in 1964, detecting such a faint signal required extraordinary care and patience. The two scientists methodically eliminated every possible source of interference they could imagine. They checked their equipment for faulty connections, loose wires, and electronic malfunctions. They considered the possibility that New York City, glowing with radio emissions just 50 miles away, might be the culprit. But the signal persisted even when they pointed the antenna away from the city, toward the emptiest patches of sky. In one of science's more amusing episodes, they even considered the possibility that pigeon droppings might be causing the interference. A pair of pigeons had taken up residence in the horn antenna, leaving what Penzias delicately described as a white dielectric material coating the interior surface. The scientists carefully cleaned the antenna, relocated the birds, and sealed off potential nesting spots. Yet still the mysterious hiss remained, unchanging and omnipresent. What Penzias and Wilson didn't immediately realize was that they had stumbled upon something cosmologists had been predicting for years. Just 30 miles away at Princeton University, a team led by Robert Dicke was actually preparing to search for this very signal. Dicke's team had been working from theoretical predictions that if the universe had indeed begun in a hot, dense state billions of years ago, the afterglow of that primordial fireball should still be detectable today, cooled by the expansion of space to just a few degrees above absolute zero. The theoretical foundation for this prediction had been laid decades earlier, though it had been largely forgotten by the scientific community. In 1948, physicists Ralph Alpha and Robert Herman had calculated that if the Big Bang theory was correct, the universe should be filled with radiation at a temperature of about 5 degrees Kelvin. Even earlier, in 1941, Canadian astronomer Andrew McKellar had observed mysterious emission lines in stellar spectra that suggested interstellar space had a temperature of about 2.3 degrees Kelvin, though he didn't connect this observation to cosmology. When Penzias and Wilson finally learned about the Princeton team's work through a chance phone conversation, the pieces of the puzzle suddenly fell into place. The persistent hiss they had been trying to eliminate wasn't noise at all. It was the oldest light in the universe, stretched and cooled by 13.8 billion years of cosmic expansion, finally reaching their antenna in Holmdel, New Jersey. The announcement of this discovery sent ripples through the scientific community that continue to this day. Published in the Astrophysical Journal in 1965, their modest paper, barely 2 pages long, carried the understated title, A Measurement of Excess Antenna Temperature at 4080 megacycles per second. This brief document, written in the dry technical language of engineering, described nothing less than humanity's first glimpse of the universe's baby picture. The implications were staggering. Here was direct physical evidence that the universe had a beginning, that it had evolved from a hot, dense state to the cool, expansive cosmos we inhabit today. The steady-state theory, which proposed that the universe had always existed in roughly its current form, with new matter continuously created to maintain constant density as space expanded, suddenly seemed untenable. The Big Bang theory, once dismissed by many as too radical, too reminiscent of religious creation stories, now had observational support that was difficult to ignore. The scientific community's response ranged from excitement to skepticism. Some cosmologists immediately recognized the significance of the discovery. Others questioned whether such a uniform background radiation could really be the remnant of the Big Bang. Perhaps it was generated by distant galaxies or by some unknown process in intergalactic space. These debates would rage for years, spurring new observations and theoretical work that would ultimately confirm and refine our understanding of the cosmic microwave background. For Penzias and Wilson, the discovery brought unexpected fame and recognition. In 1978, they were awarded the Nobel Prize in Physics, sharing it with Piotr Kapitsa, who was honoured for unrelated work in low-temperature physics. In his Nobel lecture, Penzias reflected on the serendipitous nature of their discovery, noting how they had set out to do radio astronomy and ended up doing cosmology instead. The discovery also highlighted an interesting aspect of scientific progress. While Penzias and Wilson made the observation, they initially didn't fully understand its cosmological significance. It was the theoretical work of others, particularly the Princeton team and earlier theorists, that provided the framework for interpreting what they had found. This interplay between observation and theory, between accident and intention, remains a hallmark of scientific discovery. Looking back, we can see how the discovery of the cosmic microwave background marked a turning point in cosmology. Before 1964, cosmology was largely a theoretical discipline, based more on mathematical models and philosophical arguments than on direct observation. After Penzias and Wilson's discovery, cosmology became an observational science, with precise measurements and detailed data replacing speculation and conjecture. The Horn antenna at Holmdel, now a National Historic Landmark, stands as a monument to this transformation. Visitors today can see the actual instrument that first detected the afterglow of creation, its metal surface weathered by decades of exposure, but still pointing skyward, as if continuing its eternal vigil. The site serves as a reminder that great discoveries don't always come from grand plans or expensive equipment, but sometimes from careful attention to unexpected details, from the patience to investigate anomalies that others might dismiss as mere noise. The story of how two engineers, trying to eliminate an annoying hiss from their radio antenna, ended up discovering evidence for the Big Bang, remains one of science's most compelling narratives. It demonstrates how the universe sometimes reveals its secrets in the most unexpected ways, how the faint whisper of ancient light can travel across billions of years to reach a converted satellite communication antenna in New Jersey, carrying with it the story of everything that has ever existed. To truly understand the cosmic microwave background, we must journey back to the very beginning, to those first fractions of a second when the universe burst into existence. This journey takes us through temperatures and densities so extreme that our everyday understanding of physics breaks down, where the four fundamental forces we know today were unified into a single primordial force, and where the very concepts of space and time as we understand them may not have existed at all. The story begins at what physicists call the Planck time, approximately 10 to the negative 43 seconds after the Big Bang. At this incomprehensibly brief moment, the entire observable universe was compressed into a region smaller than the Planck length, about 10 to the negative 35 meters. The temperature exceeded 10 to the 32 degrees Kelvin, a number so large that it defies meaningful comparison to anything in our current universe. At these scales and energies, quantum mechanics and general relativity, our two most successful theories of physics, come into direct conflict, suggesting that our understanding of this earliest epoch remains fundamentally incomplete. As the universe expanded and cooled through the first 10 to the negative 35 seconds, it underwent a period of exponential expansion called cosmic inflation. During this brief epoch, the universe grew by a factor of at least 10 to the 26, and possibly much more. This dramatic expansion, faster than the speed of light itself, though this doesn't violate relativity since it was space itself that was expanding, not objects moving through space, solved several puzzles about the universe's large-scale structure. It explained why the universe appears so uniform on large scales, why space appears geometrically flat, and why we don't observe certain exotic particles that should have been produced in the early universe. The energy driving this inflation came from a hypothetical field called the inflaton field, which possessed the remarkable property of gravitational repulsion. As this field slowly rolled down its potential energy curve, it drove space to expand at an ever-accelerating rate. Quantum fluctuations in this field, tiny ripples arising from the uncertainty principle, were stretched by inflation to cosmic scales. These microscopic quantum fluctuations would eventually become the seeds for all the structure we see in the universe today, from galaxies and galaxy clusters to the vast cosmic voids between them. When inflation ended, approximately 10 to the negative 32 seconds after the Big Bang, the energy stored in the inflaton field was released in a process called reheating. This energy materialized as a hot, dense soup of fundamental particles and radiation, setting the initial conditions for the hot Big Bang that followed. The temperature after reheating was approximately 10 to the 27 degrees Kelvin, still far beyond anything we can create in our most powerful particle accelerators. In these first moments, the universe was dominated by radiation and exotic particles that no longer exist in our current, cooler universe. Quarks and antiquarks materialized from pure energy and annihilated back into photons billions of times per second. Electrons and positrons danced the same violent dance of creation and destruction. The weak nuclear force and electromagnetic force were still unified into a single electroweak force, and the universe was filled with massive W and Z bosons that mediated this unified interaction. As the universe continued to expand and cool, passing through 10 to the negative 12 seconds after the Big Bang, the temperature dropped below 10 to the 15 degrees Kelvin. At this critical threshold, the electroweak force separated into the distinct electromagnetic and weak nuclear forces we observe today. This phase transition, similar to water freezing into ice but occurring in the quantum fields that permeate all of space, fundamentally changed the character of particle interactions throughout the universe. By 1 microsecond after the Big Bang, the temperature had fallen to about 10 trillion degrees Kelvin. At this point, quarks and antiquarks could no longer be spontaneously created from the ambient radiation. The slight asymmetry between matter and antimatter, about 1 extra quark for every billion quark-antiquark pairs, became crucial. As quarks and antiquarks annihilated, this tiny excess of quarks survived, eventually forming all the matter we see in the universe today. The origin of this matter-antimatter asymmetry remains one of the great unsolved mysteries in cosmology. At approximately 10 microseconds after the Big Bang, the universe underwent another crucial transition. The temperature dropped below 2 trillion degrees Kelvin, and quarks became confined into composite particles called hadrons. Protons and neutrons, the building blocks of atomic nuclei, formed for the first time. This transition, from a quark-gluon plasma to a universe filled with hadrons, marked the beginning of the universe, as we might recognize it, filled with the particles that would eventually form atoms, molecules, and everything we see around us. The next crucial epoch began at about 1 second after the Big Bang, when the temperature fell below 10 billion degrees Kelvin. At this point, neutrinos, those ghostly particles that barely interact with matter, decoupled from the rest of the universe. These primordial neutrinos continue to stream through space today, forming a cosmic neutrino background that predates even the cosmic microwave background, though it remains beyond our current ability to detect directly. Between 1 and 10 seconds after the Big Bang, the universe experienced what physicists call the period of electron-positron annihilation. As the temperature dropped below 5 billion degrees, Kelvin, electrons and their antimatter counterparts, positrons, could no longer be created from the ambient radiation. Like the quarks before them, they annihilated in vast numbers, leaving behind only a tiny excess of electrons that would eventually orbit atomic nuclei. The period from about 10 seconds to 20 minutes after the Big Bang marked the era of Big Bang nucleosynthesis, one of the great triumphs of the Big Bang model. During this time, the temperature and density of the universe were just right for nuclear fusion to occur. Protons and neutrons combined to form the first atomic nuclei: deuterium, helium-3, helium-4, and trace amounts of lithium-7. The precise abundances of these light elements, particularly the ratio of hydrogen to helium of about 3:1 by mass, provide another powerful confirmation of the Big Bang model. The physics of this nucleosynthesis era was remarkably similar to what occurs in the cores of stars today, but played out on a universal scale. Neutrons, being slightly heavier than protons, gradually decayed into protons, electrons, and antineutrinos. This decay, with a half-life of about 10 minutes, set a clock on nucleosynthesis. By the time the universe had cooled enough for complex nuclear reactions to occur, the neutron-to-proton ratio had fallen to about 1:7. This ratio, combined with the nuclear physics of fusion reactions, determined the final abundance of helium and other light elements. After nucleosynthesis ended, the universe entered a relatively quiet period that would last for hundreds of thousands of years. The universe was still too hot for atoms to form. Any electron that tried to orbit a nucleus would immediately be knocked away by energetic photons. The universe was filled with a plasma of free electrons, protons, and helium nuclei, along with an intense bath of radiation. This plasma was opaque to light, with photons constantly scattering off free electrons, unable to travel far before interacting with matter. During this era, the universe was acoustically active. Sound waves, driven by the competing forces of gravity trying to compress matter and radiation pressure, trying to expand it, propagated through the primordial plasma. These acoustic oscillations, or baryon acoustic oscillations, created regions of slightly higher and lower density. The characteristic scale of these oscillations, determined by how far sound could travel in the plasma before recombination, would later become a crucial tool for measuring cosmic distances and understanding the universe's expansion history. As we approach 380,000 years after the Big Bang, the universe had cooled to about 3,000 degrees Kelvin, roughly half the temperature of the Sun's surface. At this temperature, a remarkable transformation occurred. Electrons could finally combine with nuclei to form stable atoms without immediately being ionized by radiation. This era of recombination, despite its name suggesting that particles were combining again, actually marked the first time in the universe's history that neutral atoms could exist. The formation of neutral atoms had profound consequences for the universe. Suddenly, photons could travel freely through space without constantly scattering off free electrons. The universe became transparent for the first time. The light that was released at this moment, the surface of last scattering as astronomers call it, is the cosmic microwave background we observe today. This light has been travelling through space ever since, carrying with it a snapshot of the universe at this crucial transition. The patterns we see in the cosmic microwave background, those tiny temperature fluctuations of about 1 part in 100,000, reflect the density variations present at the time of recombination. Regions that were slightly denser appear slightly hotter, while less dense regions appear cooler. These fluctuations, though minuscule, contain the seeds of all future structure. Over billions of years, gravity would amplify these tiny variations, pulling matter into the denser regions to eventually form the first stars, galaxies, and larger structures we see today. Understanding these first moments of the universe requires us to push our theories to their absolute limits. We must extrapolate the laws of physics, tested in our laboratories at energies of perhaps 1 trillion electron volts, to energies 10 trillion times higher. We must trust that the fundamental constants of nature, the speed of light, Planck's constant, the gravitational constant, truly are constant across time and space. Yet remarkably, when we make these bold extrapolations, we find that they lead to predictions, like the existence and properties of the cosmic microwave background, that match our observations with stunning precision. The cosmic microwave background radiation that fills our universe today carries within its ancient photons a remarkable story of transformation. These particles of light have journeyed for 13.8 billion years, their wavelengths stretching with the expansion of space itself, their energy diminishing from the brilliant glow of a stellar surface to the faint whisper of microwave radiation. Understanding the physics of this ancient light requires us to explore the fundamental nature of electromagnetic radiation, the mechanics of cosmic expansion, and the subtle interplay between matter and energy that shaped the early universe. When we observe the cosmic microwave background today, we're detecting photons that last interacted with matter when the universe was approximately 380,000 years old. At that moment of last scattering, these photons had wavelengths corresponding to visible and infrared light, with a characteristic temperature of about 3,000 degrees Kelvin. The universe at this time glowed with the orange-red light, similar to a cool star, filling all of space with a uniform brilliance that would have been visible to human eyes, had any existed to witness it. The transformation of this primordial light into the microwave radiation we observe today is a direct consequence of the universe's expansion. As space itself stretches, the wavelengths of photons travelling through it stretch proportionally. This cosmological redshift differs fundamentally from the Doppler shift we encounter in everyday life. When we hear an ambulance siren change pitch as it passes by, we're experiencing a Doppler shift caused by the motion of the source through space. The cosmological redshift, by contrast, results from the expansion of space itself, stretching the very fabric through which light travels. The mathematical relationship governing this stretching is elegantly simple, yet profound in its implications. The wavelength of light scales directly with the universe's scale factor, the parameter that describes how much the universe has expanded. Since recombination, the universe has expanded by a factor of approximately 1,100. Consequently, The wavelengths of cosmic microwave background photons have stretched by this same factor, shifting from the visible spectrum deep into the microwave region of the electromagnetic spectrum. This stretching of wavelengths corresponds to a cooling of the radiation. The temperature of blackbody radiation, which the cosmic microwave background closely approximates, is inversely proportional to wavelength. As wavelengths have stretched by a factor of 1,100, the temperature has decreased by the same factor, from 3,000 degrees Kelvin at recombination to approximately 2.7 degrees Kelvin today. This precise temperature, 2.725 degrees Kelvin to be exact, represents one of the most accurately measured parameters in all of cosmology. The spectrum of the cosmic microwave background provides compelling evidence for its primordial origin. A perfect blackbody spectrum, described by Planck's law of radiation, characterizes a system in complete thermal equilibrium. The cosmic microwave background follows this theoretical curve with extraordinary precision, deviating by less than 1 part in 100,000. This near-perfect blackbody spectrum tells us that the early universe was in thermal equilibrium, with matter and radiation constantly exchanging energy through countless interactions. The establishment of this thermal equilibrium in the early universe required specific conditions that no longer exist today. In the first few 100,000 years after the Big Bang, the universe was dense enough that photons couldn't travel far before scattering off free electrons. This constant scattering, occurring billions of times per second for each photon, ensured that radiation and matter remained in thermal equilibrium. The process known as Thomson scattering involved the electromagnetic interaction between photons and charged particles, primarily electrons. The physics of Thomson's scattering played a crucial role in shaping the characteristics of the cosmic microwave background. When a photon scatters off an electron, it can exchange energy and momentum with the particle. In the hot, dense early universe, these countless scattering events redistributed energy throughout the primordial plasma, maintaining thermal equilibrium and establishing the blackbody spectrum we observe today. The cross-section for Thomson's scattering, a measure of how likely a photon is to interact with an electron, depends on fundamental constants of nature, linking the microscopic world of particle physics to the macroscopic properties of the universe. As the universe expanded and cooled, the rate of Thomson scattering gradually decreased. The mean free path of photons, the average distance they could travel before scattering, increased as the density of free electrons dropped. When the universe cooled below 3,000 degrees Kelvin and electrons combined with nuclei to form neutral atoms, the scattering rate dropped precipitously. This transition from an opaque to a transparent universe didn't happen instantaneously, but occurred over a period of about 100,000 years, creating what astronomers call the surface of last scattering. The concept of the surface of last scattering deserves careful consideration. Unlike a physical surface, it represents a moment in time rather than a location in space. When we observe the cosmic microwave background, we're looking back through time to see the universe as it was everywhere at the moment of recombination. The photons we detect today have travelled from a spherical shell centred on our location, with a radius determined by the distance light has travelled since recombination. Every observer in the universe sees their own surface of last scattering, their own unique view of the universe at this crucial epoch. The polarization of cosmic microwave background photons adds another layer of physical richness to this ancient light. Polarization, a property describing the orientation of electromagnetic waves, arises from the scattering processes in the early universe. When photons undergo Thomson scattering in the presence of a quadrupole anisotropy in the radiation field, they acquire a net polarization. This polarization pattern, detected by sensitive modern instruments, provides additional information about the physics of the early universe and the formation of structure. The generation of polarization in the cosmic microwave background involves subtle physics that connects quantum mechanics to cosmology. At the time of last scattering, local variations in temperature and density created anisotropies in the radiation field. When photons scattered off electrons in these anisotropic environments, they preferentially scattered in certain directions, creating a net polarization. The pattern of this polarization across the sky encodes information about the velocity fields and density gradients present at recombination. Two distinct patterns of polarization, called E modes and B modes by analogy with electric and magnetic fields, carry different cosmological information. E mode polarization, which has been detected with high precision, arises from scalar perturbations in the early universe, the density fluctuations that seeded structure formation. B mode polarization, much fainter and more challenging to detect, can arise from primordial gravitational waves generated during cosmic inflation or from gravitational lensing of E modes by intervening matter. The search for primordial B mode polarization represents one of the holy grails of modern cosmology. These patterns, if detected, would provide direct evidence for gravitational waves from the inflationary epoch, offering a window into the universe when it was only 10 to the negative 35 seconds old. The amplitude of these primordial gravitational waves depends on the energy scale of inflation, potentially allowing us to probe physics at energies far beyond what any particle accelerator could achieve. The interaction between cosmic microwave background photons and matter didn't entirely cease at recombination. As these ancient photons travel through the universe, they encounter various forms of matter and energy that can alter their properties. The Sunyaev-Zeldovich effect, for instance, occurs when cosmic microwave background photons pass through hot gas in galaxy clusters. High-energy electrons in the cluster gas can boost the energy of these photons through inverse Compton scattering, creating a characteristic distortion in the cosmic microwave background spectrum. Gravitational lensing provides another mechanism through which the cosmic microwave background is modified during its journey to our detectors. As photons travel through the universe, they pass by massive structures whose gravity bends their paths. This deflection, predicted by Einstein's general relativity, creates subtle distortions in the cosmic microwave background temperature and polarization patterns. These lensing effects, while complicating the interpretation of primordial signals, also provide valuable information about the distribution of matter, including dark matter, along the line of sight. The Sachs-Wolf effect represents yet another physical process affecting cosmic microwave background photons. This effect, which comes in both ordinary and integrated varieties, describes how photons gain or lose energy as they climb out of or fall into gravitational potential wells. The ordinary Sachs-Wolf effect occurred at the time of last scattering, with photons in denser regions having to climb out of deeper gravitational wells, losing energy and appearing cooler. The integrated Sachs-Wolf effect occurs as photons travel through the evolving gravitational landscape of the universe, gaining or losing energy as potential wells deepen or shallow due to cosmic expansion and structure formation. Understanding these various physical effects requires sophisticated theoretical frameworks that combine general relativity, quantum mechanics, thermodynamics, and plasma physics. The Boltzmann equation, a fundamental tool in statistical mechanics, describes how the distribution of photons evolves in the expanding universe. Solving this equation in the presence of matter, including dark matter and baryons, requires numerical techniques and powerful computers, especially when including all the relevant physical processes. The physics of the cosmic microwave background also involves subtle quantum mechanical effects. The statistics of the temperature fluctuations, for instance, are believed to originate from quantum fluctuations during cosmic inflation. These quantum fluctuations, stretched to macroscopic scales by inflation, transitioned from quantum to classical during or shortly after inflation, seeding the density perturbations we observe today. This quantum to classical transition, still not fully understood, represents one of the most remarkable aspects of cosmology, linking the microscopic quantum world to the largest structures in the universe. The cosmic microwave background photons that reach our detectors today have undertaken one of the most extraordinary journeys imaginable, travelling through space and time for 13.8 billion years. This odyssey has taken them through the evolving cosmos, past forming galaxies, through vast cosmic voids, and around massive galaxy clusters. Their journey tells the story of the universe's evolution, from a smooth, nearly uniform plasma to the rich, structured cosmos we observe today. When these photons began their journey at the moment of recombination, the universe was a vastly different place than it is today. There were no stars, no galaxies, no planets. The universe consisted almost entirely of hydrogen and helium atoms, with trace amounts of lithium spread nearly uniformly through space. The density variations that existed were tiny, perhaps 1 part in 100,000, barely visible as slight temperature differences in the cosmic microwave background. Yet these minute fluctuations contained the seeds of all future cosmic structure. As the cosmic microwave background photons began their journey, streaming freely through space for the first time, the universe entered what cosmologists call the Dark Ages. This period, lasting from recombination at 380,000 years after the Big Bang until the formation of the first stars, perhaps 100 million years later, represents one of the least understood epochs in cosmic history. During this time, the universe was truly dark, filled only with neutral hydrogen and helium gas and the gradually cooling cosmic microwave background radiation. Throughout the Dark Ages, gravity was quietly at work, amplifying those tiny initial density fluctuations. Regions that were slightly denser than average attracted surrounding matter, growing denser still. This gravitational instability, first described mathematically by James Jeans in the early 20th century, operated on all scales. From small clumps that would eventually form individual galaxies to vast regions that would become galaxy clusters and superclusters. Dark matter, which had begun clustering even before recombination since it doesn't interact with photons, provided the gravitational scaffolding around which ordinary matter would accumulate. The cosmic microwave background photons travelling through this evolving universe experienced the changing gravitational landscape. As they passed through regions where matter was accumulating, they gained energy falling into gravitational wells and lost energy climbing out. In a static universe, these effects would cancel perfectly. However, in our expanding universe where structures grow with time, the cancellation is imperfect. This integrated Sachs-Wolf effect leaves subtle imprints on the cosmic microwave background, particularly on large angular scales. Approximately 100 million years into their journey, the cosmic microwave background photons would have witnessed a transformative event, the birth of the first stars. These primordial stars, formed from pristine hydrogen and helium gas, were likely much more massive than typical stars today, perhaps hundreds of times the mass of our Sun. They burned bright and hot, emitting intense ultraviolet radiation that began to ionize the neutral hydrogen gas surrounding them. This marked the beginning of the epoch of ionization, a pivotal transition in cosmic history. The process of ionization fundamentally altered the universe through which cosmic microwave background photons travelled. As energetic photons from the first stars and galaxies ionized hydrogen atoms, splitting them back into free protons and electrons, the universe once again became filled with free charges. This had profound consequences for the cosmic microwave background. A small fraction of the background photons, about 5 to 10%, scattered off these newly liberated electrons, slightly suppressing temperature fluctuations on small scales and generating new polarization patterns. The ionization of the universe didn't happen uniformly or instantaneously. It began around the first stars and galaxies, creating expanding bubbles of ionized gas in a sea of neutral hydrogen. These ionization fronts propagated outward, eventually overlapping and merging until, by about 1 billion years after the Big Bang, the entire universe was ionized. The cosmic microwave background photons passing through this patchy, evolving ionization field experienced varying amounts of scattering encoding information about the reionization process in their polarization patterns. As cosmic microwave background photons continued their journey, the universe underwent dramatic structural evolution. Small galaxies merged to form larger ones. Galaxy clusters assembled from the merger of galaxy groups, and vast filaments of matter formed, creating the cosmic web we observe today. This hierarchical structure formation, driven by gravity and influenced by dark energy, created an increasingly complex environment through which the background photons travelled. The formation of galaxy clusters, the largest gravitationally bound structures in the universe, had particularly notable effects on passing cosmic microwave background photons. As photons pass through the hot gas that fills galaxy clusters, they underwent inverse Compton scattering with high-energy electrons. This Sunyaev-Zeldovich effect, predicted theoretically in 1969 and first observed in 1978, boosts the energy of some photons, creating a characteristic distortion in the cosmic microwave background spectrum toward galaxy clusters. The journey of cosmic microwave background photons also took them through vast cosmic voids, regions of space containing very few galaxies. These voids, which can span hundreds of millions of light-years, represent the underdense regions that complemented the overdense regions where galaxies formed. The existence and properties of these voids, traced by the galaxies that outline their boundaries, provide important tests of our understanding of structure formation and the nature of dark energy. About 5 billion years into their journey, cosmic microwave background photons would have experienced another fundamental change in the universe's evolution. Dark energy, that mysterious component that makes up about 70% of the universe's energy density today, began to dominate over matter. This transition from matter domination to dark energy domination marked the beginning of accelerated cosmic expansion. Structures that were gravitationally bound, like galaxies and galaxy clusters, remained intact, but the expansion of space between these structures began to accelerate. The influence of dark energy on cosmic microwave background photons is subtle but measurable. Through the late-time integrated Sachs-Wolf effect, photons gain a small amount of energy when passing through large-scale structures in an accelerating universe. This effect, first detected in 2003 by correlating cosmic microwave background maps with galaxy surveys, provides independent evidence for dark energy and helps constrain its properties. As cosmic microwave background photons approached our region of the universe, they encountered the local group, our small cluster of galaxies including the Milky Way, Andromeda, and several dozen smaller galaxies. The gravitational field of the local group creates a dipole pattern in the cosmic microwave background, making it appear slightly hotter in the direction we're moving toward and cooler in the direction we're moving away from. This dipole, with an amplitude of about 3 millikelvin, tells us that our galaxy is moving at approximately 600 kilometers per second relative to the cosmic microwave background rest frame. The final leg of the journey for cosmic microwave background photons involves passing through our own galaxy, the Milky Way. Dust grains in the interstellar medium can absorb and re-emit these photons, creating foreground contamination that must be carefully removed from cosmic microwave background maps. Synchrotron radiation from relativistic electrons spiraling in the galaxy's magnetic field and free emission from ionized gas add additional foreground signals that must be separated from the primordial cosmic microwave background signal. Even in the final moments of their journey, as cosmic microwave background photons enter our solar system and Earth's atmosphere, they face additional challenges. Water vapor in Earth's atmosphere absorbs microwave radiation, which is why ground-based cosmic microwave background observations are typically conducted from high, dry locations like the Atacama Desert in Chile or the South Pole. Space-based observatories avoid these atmospheric effects entirely, providing the cleanest views of the cosmic microwave background. The detection of these much-travelled photons requires sophisticated technology and careful calibration. Modern cosmic microwave background detectors use superconducting sensors cooled to within a fraction of a degree of absolute zero, necessary to detect the faint microwave signals without adding thermal noise. These detectors must be sensitive to temperature differences of just a few microkelvin, requiring extraordinary precision in both design and operation. The journey of cosmic microwave background photons also carries information about fundamental physics that we're only beginning to decode. The patterns in the cosmic microwave background may contain signatures of physics beyond the standard model, evidence for extra dimensions, or clues about the nature of dark matter and dark energy. Some theories predict that cosmic strings, hypothetical one-dimensional defects in spacetime, might have left distinctive patterns in the cosmic microwave background as photons travelled past them. The statistical properties of the cosmic microwave background fluctuations tell us about the physics of the very early universe. The nearly Gaussian distribution of temperature fluctuations supports the inflationary paradigm, where quantum fluctuations in a scalar field were stretched to cosmic scales. Small deviations from perfect Gaussian statistics, called non-Gaussianity, could reveal details about the physics of inflation or alternative theories of the early universe. As we trace the journey of individual photons, we must remember that we're observing a statistical ensemble. Each photon that reaches our detectors has its own unique history, its own path through the cosmic web, its own encounters with matter and energy. Yet collectively, these photons create a remarkably coherent picture, a snapshot of the universe at recombination that has been subtly modified by their subsequent journey. The concept of the cosmic microwave background as a backlight for the universe has proven particularly powerful. Just as a medical X-ray reveals internal structure by passing radiation through the body, the cosmic microwave background illuminates the structure of the universe along our line of sight. Galaxy clusters appear as shadows or bright spots depending on the physical process involved. Gravitational lensing creates distortion patterns that map the distribution of dark matter, and the integrated Sachs-Wolf effect traces the growth of structure over cosmic time. The journey of cosmic microwave background photons connects the smallest and largest scales in physics. quantum fluctuations smaller than an atom in the early universe have been stretched to patterns spanning billions of light-years. Photons that were once in thermal equilibrium, constantly interacting with matter, have travelled freely for billions of years, carrying information across cosmic time. This connection between the quantum and the cosmic, the microscopic and the universal, represents one of the most profound aspects of modern cosmology. The task of mapping the cosmic microwave background represents one of the most ambitious scientific endeavours ever undertaken, requiring us to create detailed charts of radiation that fills the entire sky with nearly perfect uniformity. These maps, built from billions of individual measurements, reveal the invisible architecture of the early universe, structures that would eventually evolve into the galaxies, clusters, and cosmic web we observe today. The process of creating and interpreting these maps combines cutting-edge technology, sophisticated data analysis, and deep theoretical understanding. The first attempts to map the cosmic microwave background beyond the initial discovery by Penzias and Wilson began in the late 1970s and early 1980s. These early experiments, using ground-based and balloon-borne instruments, could only map small portions of the sky with limited sensitivity. They searched for anisotropies, variations in the temperature of the cosmic microwave background across different directions, but initially found only the dipole caused by our motion through space. The cosmic microwave background appeared frustratingly uniform, leading some scientists to question whether the fluctuations predicted by theory actually existed. The breakthrough came with the Cosmic Background Explorer satellite, known as COBE, launched by NASA in 1989. COBE carried 3 instruments designed to study different aspects of the cosmic microwave background. The far-infrared absolute spectrophotometer measured the spectrum, confirming with unprecedented precision that it followed a perfect blackbody curve. The diffuse infrared background experiment searched for infrared radiation from the first stars and galaxies. Most importantly for cosmology, the differential microwave radiometer created the first all-sky maps of the cosmic microwave background temperature. COBE's maps revealed what ground-based experiments had struggled to find: tiny temperature fluctuations at the level of about 1 part in 100,000. These fluctuations, announced to great fanfare in 1992, showed that the early universe was not perfectly smooth, but contained the density variations needed to seed structure formation. The patterns in these fluctuations, analysed using sophisticated statistical techniques, matched the predictions of inflationary cosmology, providing strong support for this theory of the universe's earliest moments. The angular resolution of COBE, about 7 degrees, was relatively coarse, showing only the larger scale patterns in the cosmic microwave background. To understand the physics of the early universe in greater detail, cosmologists needed maps with much finer angular resolution. This drove the development of a new generation of ground-based and balloon-borne experiments in the 1990s, including the Atacama Cosmology Telescope, the South Pole Telescope, and the balloon-borne Boomerang and Maxima experiments. These experiments focused on measuring the cosmic microwave background power spectrum, a statistical description of how the amplitude of temperature fluctuations varies with angular scale. The power spectrum revealed a series of peaks and troughs, acoustic oscillations frozen into the cosmic microwave background at the time of recombination. The position and amplitude of these peaks depend on fundamental cosmological parameters, including the density of ordinary matter, dark matter, and dark energy, the geometry of space, and the expansion rate of the universe. The first acoustic peak, occurring at an angular scale of about 1 degree, corresponds to regions that had undergone exactly one compression when recombination occurred. The second peak represents regions that had compressed and then rarefied once. The third peak regions that had compressed, rarefied, and compressed again, and so on. The relative heights of these peaks depend on the baryon density, with odd-numbered peaks enhanced and even-numbered peaks suppressed as baryon density increases. This pattern provides a precise measure of the amount of ordinary matter in the universe. The Wilkinson Microwave Anisotropy Probe, or WMAP, launched by NASA in 2001, revolutionized cosmic microwave background mapping. Positioned at the second Lagrange point, 1.5 million kilometers from Earth in the anti-sun direction, WMAP could observe the entire sky without interference from Earth's heat or the sun's radiation. Over 9 years of observations, WMAP created increasingly detailed maps of the cosmic microwave background temperature, and for the first time from space, its polarization. WMAP's maps revealed the cosmic microwave background in exquisite detail, with angular resolution of about 13 arc-minutes at its highest frequency. The mission measured cosmological parameters with unprecedented precision, determining the age of the universe to be 13.77 billion years, with an uncertainty of only 40 million years. WMAP found that ordinary matter makes up only 4.6% of the universe's energy density, dark matter 23%, and dark energy 72%. These measurements transformed cosmology from a field of order of magnitude estimates to a precision science. The Planck satellite, launched by the European Space Agency in 2009, pushed cosmic microwave background mapping to even greater heights. With 9 frequency channels ranging from 30 to 857 GHz, Planck could separate cosmic microwave background signals from foreground contamination with unprecedented accuracy. Its angular resolution, reaching 5 arc-minutes at the highest frequencies, revealed structures in the cosmic microwave background invisible to previous missions. Planck's maps contain an enormous amount of information, requiring sophisticated analysis techniques to extract. The raw data from the satellite's detectors must be carefully calibrated, with corrections for instrumental effects, cosmic ray hits, and systematic errors. The different frequency channels must be combined to separate the cosmic microwave background from foreground emissions, including synchrotron radiation from our galaxy, thermal dust emission, and free radiation from ionized gas. This component separation process uses the different spectral signatures of these emissions to isolate the cosmic microwave background signal. The creation of cosmic microwave background maps also requires careful attention to the scanning strategy of the observing instrument. Satellites like WMAP and Planck spin continuously, with their spin axes precessing to cover the entire sky over months or years. This scanning pattern must be designed to provide uniform sky coverage while minimizing systematic errors. Ground-based telescopes face additional challenges, as they can only observe the portion of sky visible from their location and must deal with atmospheric emission and absorption. The statistical analysis of cosmic microwave background maps employs powerful mathematical tools developed from various fields of physics and mathematics. Spherical harmonic decomposition, analogous to Fourier analysis on a sphere, allows scientists to separate fluctuations on different angular scales. The correlation function quantifies how temperature fluctuations at different points on the sky relate to each other. Maximum likelihood estimation and Bayesian inference extract cosmological parameters from the observed patterns, accounting for instrumental noise and cosmic variance, the fundamental statistical uncertainty arising from observing only one realization of the universe. The maps reveal fascinating features beyond the primary temperature fluctuations. Cold spots and hot spots mark regions that were over or under dense at recombination. The cold spot, a particularly large cold region in the constellation Eridanus, has sparked considerable scientific interest and speculation. Some scientists propose it could be evidence for exotic physics, perhaps a texture or other topological defect from the early universe, though most favour more conventional explanations involving the integrated Sachs-Wolf effect from a large cosmic void. Polarization maps add another dimension to our view of the cosmic microwave background. The polarization patterns, typically about 10% as strong as the temperature fluctuations, arise from Thomson scattering of anisotropic radiation at the time of recombination and reionization. These patterns are conventionally decomposed into E modes, which have even parity, and B modes, which have odd parity. E mode polarization has been mapped with increasing precision, providing independent confirmation of the acoustic oscillation pattern seen in temperature fluctuations. The search for B mode polarization has driven the development of increasingly sensitive instruments. Primordial B modes, if they exist, would be evidence for gravitational waves from cosmic inflation, but they're expected to be extremely faint, perhaps less than 100 nanokelvin in amplitude. Several experiments have detected B mode polarization from gravitational lensing of E modes, demonstrating that the technology exists to measure these faint signals. The search for primordial B modes continues with experiments like Bicep Keck Array at the South Pole, the Simons Observatory in Chile, and proposed future satellites. The challenge of foreground removal becomes particularly acute in polarization measurements. Galactic dust grains, aligned by magnetic fields, emit polarized radiation that can mimic the cosmic microwave background signal. The spectacular announcement in 2014 of primordial B-mode detection by the Bicep 2 experiment, later shown to be contaminated by dust emission, highlighted the importance of multi-frequency observations for reliable foreground separation. Modern cosmic microwave background maps contain so much information that new analysis techniques continue to reveal previously hidden features. Machine learning algorithms can identify subtle patterns that traditional analysis might miss. Topological analysis examines the connectivity of hot and cold regions, searching for signatures of non-trivial cosmic topology or primordial non-Gaussianity. Stacking analyses combine signals from many similar regions, such as the locations of galaxy clusters or cosmic voids, to detect effects too weak to see individually. The combination of cosmic microwave background maps with other cosmological observations has proven particularly powerful. Cross-correlating cosmic microwave background maps with galaxy surveys reveals the integrated Sachs-Wolf effect and gravitational lensing signals. Combining cosmic microwave background data with supernovae observations and baryon acoustic oscillation measurements from galaxy surveys provides tight constraints on dark energy properties. This multi-probe approach has become standard in modern cosmology, with different observations providing complementary information about the universe. The maps also serve as a backdrop for studying intervening structures. The Sunyaev-Zeldovich effect allows astronomers to detect galaxy clusters through their imprint on the cosmic microwave background, even at very high redshifts, where the galaxies themselves are too faint to observe directly. Gravitational lensing of the cosmic microwave background reveals the distribution of all matter, including dark matter, along the line of sight. These secondary effects transform cosmic microwave background maps from static pictures of the early universe into dynamic probes of cosmic evolution. Looking at these maps, we see patterns that span the entire sky structures larger than any individual galaxy or cluster, patterns that encode the physics of the universe when it was less than 400,000 years old. Each pixel in these maps represents a direction on the sky, a line of sight extending back 13.8 billion years to the surface of last scattering. The temperature measured in each pixel, typically about 2.725 degrees, Kelvin plus or minus a few hundred microkelvin, tells us about the density, velocity, and gravitational potential at that location in the early universe. The detection and measurement of the cosmic microwave background radiation represents one of the most remarkable technological achievements in modern science. The challenge is formidable. We must detect radiation that has cooled to less than 3 degrees above absolute zero, measure temperature variations of just a few parts per million, and separate this ancient signal from numerous sources of interference, both cosmic and terrestrial. The instruments developed for this task push the boundaries of what is technologically possible, employing quantum mechanical effects, superconducting materials, and sophisticated signal processing techniques. The fundamental challenge in detecting the cosmic microwave background lies in its extreme faintness. The total power received from the cosmic microwave background is about 1 million times weaker than the signal from a typical cell phone. The temperature fluctuations we seek to measure are typically just tens of microkelvin, requiring detectors sensitive to temperature differences smaller than 100,000th of a degree. Achieving this sensitivity demands not just exceptional detectors, but entire systems optimized for minimizing noise and maximizing signal fidelity. The evolution of detector technology for cosmic microwave background observations reflects broader advances in physics and engineering. The earliest observations, including the discovery by Penzias and Wilson, used coherent amplifiers similar to those in radio receivers. These devices amplified the incoming microwave signal while adding as little noise as possible. The fundamental limit for such amplifiers is set by quantum mechanics, specifically the uncertainty principle, which dictates that any amplifier must add noise equivalent to at least half a photon per mode. Modern coherent receivers use high electron mobility transistor amplifiers, or HEMTs, cooled to cryogenic temperatures to minimize thermal noise. These devices, operating at temperatures of a few Kelvin, can achieve noise temperatures, a measure of added noise expressed as an equivalent temperature, approaching the quantum limit. The low-noise amplifiers used in cosmic microwave background experiments represent some of the most sensitive amplifiers ever created, capable of detecting signals corresponding to temperature changes of just a few microkelvin. The transition from coherent receivers to bolometric detectors marked a major advance in cosmic microwave background technology. Bolometers measure the total power of incoming radiation by detecting the tiny temperature rise it produces in an absorber. For cosmic microwave background observations, these devices typically consist of a small absorber, often a spider web-like mesh of silicon nitride coated with metal, connected to a heatsink through a weak thermal link. Incoming radiation heats the absorber, and this temperature rise is measured by a sensitive thermometer. The thermometers in modern bolometers exploit various physical phenomena to achieve extraordinary sensitivity. Transition edge sensors use the sharp change in resistance that occurs when a superconductor transitions to its normal state. By operating right at this transition temperature, typically around 100 millikelvin for cosmic microwave background applications, these devices can detect temperature changes of less than a microkelvin. The physics of superconductivity, a purely quantum mechanical phenomenon, thus enables the detection of the faint whispers from the early universe. Neutron transmutation doped germanium, Thermistors provide another approach to sensitive thermometry. These devices use germanium crystals that have been exposed to neutron radiation, creating a precise concentration of dopant atoms. The resistance of these thermistors varies strongly with temperature at cryogenic temperatures, providing excellent sensitivity. The manufacturing process requires careful control, with the germanium exposed to neutron flux in nuclear reactors to achieve the exact doping levels needed for optimal performance. Kinetic inductance detectors represent a newer technology that has shown great promise for cosmic microwave background observations. These devices use the change in the kinetic inductance of a superconductor when photons break Cooper pairs, the paired electrons that carry current without resistance in superconductors. By incorporating the superconductor into a resonant circuit, tiny changes in inductance can be detected as shifts in resonance frequency. Multiple detectors can be read out on a single line using frequency division multiplexing, greatly simplifying the wiring requirements for large detector arrays. The cooling systems required for these ultra-sensitive detectors represent remarkable achievements in their own right. Dilution refrigerators, which use the phase separation of helium-3 and helium-4 mixtures, can reach temperatures below 10 millikelvin. These complex machines require careful design and operation, with multiple cooling stages to intercept heat loads from warmer components. The vibration isolation needed to prevent mechanical noise from warming the detectors adds another layer of complexity. For space-based missions, cooling presents unique challenges. Without access to liquid cryogens that would eventually boil away, satellites must use mechanical coolers or stored cryogens with finite lifetimes. The Planck satellite used a complex cooling chain, starting with passive radiators cooling to about 50 Kelvin, followed by a sorption cooler reaching 4 Kelvin, and finally a dilution refrigerator achieving 100 millikelvin at the detectors. This system operated flawlessly for over 2.5 years, limited ultimately by the supply of helium-3 and helium-4. The optical systems that focus cosmic microwave background radiation onto detectors require careful design to minimize systematic errors and maximize sensitivity. Most modern experiments use offset Gregorian or Dragone telescopes, designs that minimize instrumental polarization and provide a wide field of view. The mirrors must be precisely shaped to focus radiation while maintaining low side lobe levels, minimizing pickup from the ground or other sources of interference. The materials used in cosmic microwave background optics present their own challenges. Mirrors must maintain their shape, despite temperature variations, requiring materials with low thermal expansion coefficients or active control systems. For refracting optics, materials transparent to microwave radiation include high-density polyethylene, silicon, and alumina. Anti-reflection coatings, often consisting of metamaterials or precisely machined surface structures, minimize losses and reflections that could create systematic errors. Polarization modulators play a crucial role in many cosmic microwave background experiments. Half-wave plates, which rotate the polarization of incoming radiation, allow the separation of polarized from unpolarized signals and the mitigation of systematic errors. These devices, often made from birefringent materials like sapphire or metamaterials, must be precisely manufactured and controlled. Rotating half-wave plates can modulate the polarization signal at frequencies above atmospheric fluctuations and other sources of low-frequency noise. The readout electronics for cosmic microwave background detectors must amplify and digitize tiny signals while adding minimal noise. Superconducting quantum interference devices, or SQUIDs, provide the first stage of amplification for many bolometric detectors. These devices use quantum mechanical effects in superconducting loops to achieve extraordinary sensitivity to magnetic fields, which can be coupled to the current or voltage changes in the detectors. Digital electronics must sample the detector outputs at rates sufficient to capture all relevant information while managing enormous data rates. Modern experiments can generate terabytes of data per day, requiring sophisticated data acquisition systems and real-time processing capabilities. Field programmable gate arrays, or FPGAs, provide flexible, high-speed processing for tasks like demodulation, filtering, and compression. The challenge of multiplexing, reading out many detectors with a limited number of wires and amplifiers, has driven significant technological development. Frequency division. Multiplexing assigns each detector a unique frequency, allowing many signals to be combined on a single line. Time division multiplexing rapidly switches between detectors, reading each in sequence. Digital frequency division multiplexing combines resonant detectors with digital signal processing for efficient readout of large arrays. Magnetic shielding presents another crucial technological challenge. The Earth's magnetic field and variations in it can couple to superconducting components, creating noise and systematic errors. Multi-layer shields using high permeability materials like mu metal combined with superconducting shields can reduce magnetic fields by factors of millions. The design of these shields must balance effectiveness with practical constraints like weight and thermal considerations. The control and monitoring systems for cosmic microwave background experiments require exceptional stability and precision. Temperature controllers must maintain detectors at fixed temperatures with microkelvin stability. Pointing systems must track celestial sources with arc-second precision while scanning smoothly to create uniform sky coverage. Housekeeping systems monitor hundreds or thousands of parameters, from temperatures and pressures to voltages and currents, ensuring all components operate within specifications. Calibration systems provide the absolute reference needed to convert detector outputs to physical units. Thermal calibration sources, essentially blackbody radiators at known temperatures, provide one approach. Electronic calibration involves injecting known signals into the detection chain. Astronomical calibrators include planets, which provide bright, well-characterized microwave sources, and the dipole from our motion through the cosmic microwave background, which provides an all-sky calibration signal. The development of large detector arrays has transformed cosmic microwave background observations. While early experiments use single detectors or small arrays, modern instruments employ thousands of detectors operating simultaneously. The polar bear experiment uses over 7,000 detectors, while proposed future experiments envision arrays with hundreds of thousands of detectors. These large arrays require mass production techniques adapted from the semiconductor industry, including photolithography and micromachining. The testing and characterization of cosmic microwave background instruments requires specialized facilities and techniques. Cryogenic test DWARs allow detector characterization at operating temperatures. Anechoic chambers lined with microwave-absorbing material enable optical testing without reflections. Fourier transform spectrometers measure the spectral response of detectors and optical components. Environmental test chambers subject instruments to the temperature extremes and vacuum conditions they will experience in operation. The intricate patterns encoded in the cosmic microwave background radiation contain a wealth of information about the universe's composition, geometry, history, and ultimate fate. These patterns, revealed through decades of increasingly precise observations, have transformed our understanding of cosmology from qualitative descriptions to quantitative science. Each feature in the cosmic microwave background maps, from the larger scale fluctuations spanning the entire sky to the smallest ripples we can detect, tells us something specific about the physics of the early universe and the fundamental parameters that govern cosmic evolution. The most prominent pattern in the cosmic microwave background is the dipole anisotropy, a smooth variation across the sky with one hemisphere appearing about 3 millikelvin warmer than the opposite hemisphere. This dipole results from our motion through space at approximately 600 kilometers per second, relative to the cosmic rest frame defined by the cosmic microwave background. The direction and magnitude of this motion tell us about the gravitational influences acting on our galaxy, including the pull of nearby galaxy clusters and larger structures like the Great Attractor, a gravitational anomaly in intergalactic space, tens of thousands of times more massive than our galaxy. Beyond the dipole, the temperature fluctuations in the cosmic microwave background follow specific statistical patterns that encode information about the early universe. The angular power spectrum, which quantifies the amplitude of fluctuations as a function of angular scale, reveals a series of acoustic peaks. These peaks represent acoustic oscillations in the primordial plasma, frozen at the moment of recombination. The position of the first peak, at approximately 1 degree on the sky, tells us about the geometry of space itself. In a flat universe, where parallel lines remain parallel forever and the angles of a triangle sum to exactly 180 degrees, the first acoustic peak appears at a specific angular scale determined by the sound horizon at recombination. If space were positively curved like the surface of a sphere, the peak would shift to larger angular scales. If space were negatively curved like a saddle, it would shift to smaller scales. Observations show the peak exactly where expected for a flat universe, confirming with exquisite precision that space on large scales follows Euclidean geometry. The relative heights of the acoustic peaks provide a cosmic baryon census. Baryons, ordinary matter made of protons and neutrons, add mass to the oscillating fluid in the early universe, enhancing compression peaks and suppressing rarefaction peaks. This creates an alternating pattern in peak heights that depends on the baryon density. Measurements show that baryons constitute only about 5% of the universe's total energy density, with the exact value determined to be 4.9% with an uncertainty of just a few percent. The damping of power on small angular scales tells us about the process of recombination itself. Recombination didn't happen instantaneously, but occurred over thousands of years as the universe cooled through the temperature range where hydrogen atoms could form. During this extended period, photons could diffuse through the partially ionized plasma, smoothing out fluctuations on small scales. This silk damping, named after astronomer Joseph Silk, who first described it, creates an exponential suppression of power at high multipoles in the angular power spectrum. The amplitude of the fluctuations at different scales constrains the primordial power spectrum, the initial distribution of density perturbations created in the very early universe. Observations show this primordial spectrum is nearly scale invariant, with almost equal power on all scales, but with a slight tilt that gives more power to larger scales. This spectral index, measured to be about 0.965, provides crucial evidence for cosmic inflation, which predicts just such a slight deviation from perfect scale invariance. Polarization patterns in the cosmic microwave background provide independent confirmation of the acoustic oscillation picture and reveal additional information about the early universe. E-mode polarization peaks are out of phase with temperature peaks, as expected from the physics of Thomson scattering in the presence of quadrupole radiation patterns. The amplitude of polarization relative to temperature fluctuations depends on the thickness of the last scattering surface and the degree of anisotropy in the radiation field at recombination. The large-scale polarization of the cosmic microwave background tells us about rionization, the epoch when the first stars and galaxies ionized the intergalactic medium. This rionization created a new scattering surface for cosmic microwave background photons, suppressing temperature fluctuations and generating polarization on large angular scales. The optical depth to rionization, measured from the large-scale polarization signal, indicates that rionization occurred when the universe was about 400 million years old, much earlier than the first galaxies we can directly observe. The search for primordial B-mode polarization continues to captivate cosmologists, as these patterns would provide direct evidence for gravitational waves from cosmic inflation. The amplitude of these primordial B-modes depends on the energy scale of inflation, with higher energy inflation producing stronger gravitational waves. Current upper limits constrain the tensor to scalar ratio, which compares the amplitude of gravitational waves to density fluctuations, to be less than about 0.06, implying that inflation occurred at energies below about 2 × 10 to the 16 GeV. Secondary anisotropies in the cosmic microwave background, created as photons travel through the evolving universe, provide additional cosmological information. The integrated Sachs-Wolf effect, caused by the evolution of gravitational potentials along the line of sight, creates correlations between the cosmic microwave background and the distribution of galaxies. This effect, which is particularly strong in a universe dominated by dark energy, provides independent evidence for cosmic acceleration. The Sunyaev-Zeldovich effect from galaxy clusters creates both a thermal effect, where hot electrons boost the energy of cosmic microwave background photons, and a kinetic effect from the bulk motion of clusters. These effects allow astronomers to detect galaxy clusters independent of their redshift, providing a powerful tool for studying cluster evolution and cosmology. The number of clusters detected through their Sunyaev-Zeldovich signature constrains the amplitude of matter fluctuations and the dark energy equation of state. Gravitational lensing of the cosmic microwave background by intervening matter creates subtle distortions in both temperature and polarization patterns. These lensing signals have now been detected with high significance, providing maps of the integrated matter distribution along the line of sight. The lensing power spectrum constrains the sum of neutrino masses, as massive neutrinos suppress structure formation on small scales, reducing the lensing signal. The statistics of cosmic microwave background fluctuations test fundamental assumptions about the early universe. The fluctuations are observed to be highly Gaussian, meaning they follow a normal distribution, consistent with the prediction that they originated from quantum fluctuations during inflation. Searches for non-Gaussianity, deviations from this normal distribution, could reveal information about the physics of inflation or alternative theories of the early universe. The cosmic microwave background also constrains the topology of the universe. If the universe were finite with a non-trivial topology, like a 3 torus or more exotic shapes, we would see matching patterns on opposite sides of the sky, where our view wraps around the universe. Searches for such matched circles or other topological signatures have found no evidence for a small universe, implying that if the universe is finite, it must be much larger than our observable horizon. Measurements of the cosmic microwave background have determined the age of the universe with remarkable precision. The acoustic peak structure, combined with measurements of the expansion rate, yields an age of 13.797 billion years, with an uncertainty of only 21 million years. This precise age determination has resolved long-standing paradoxes, confirming that the universe is indeed older than the oldest stars we observe. The cosmic microwave background provides our most precise measurement of the universe's composition. Combined analysis of temperature and polarization data shows that the universe consists of approximately 4.9% ordinary matter, 26.8% dark matter, and 68.3% dark energy. These percentages are known to better than a few percent accuracy, a remarkable achievement considering that dark matter and dark energy remain mysterious in terms of their fundamental nature. The constraints on dark matter from the cosmic microwave background are particularly interesting. The acoustic oscillations show that dark matter was already clustered at recombination, having begun gravitational collapse much earlier since it doesn't interact with photons. The ratio of dark matter to ordinary matter, about 5.4 to 1, is determined with high precision. The cosmic microwave background also constrains dark matter properties, ruling out certain models where dark matter interacts significantly with photons or itself. For dark energy, the cosmic microwave background provides complementary information to other probes like supernovae. While the primary cosmic microwave background anisotropies are mainly sensitive to the dark energy density, secondary effects like the integrated Sachs-Wolf effect and the impact on the growth of structure provide information about the dark energy equation of state. Current data are consistent with dark energy being a cosmological constant, but there's room for alternative models with slowly varying dark energy. The combination of cosmic microwave background data with other cosmological observations has proven particularly powerful. When combined with measurements of baryon acoustic oscillations in galaxy surveys and Type Ia supernovae distances, the constraints on cosmological parameters tighten considerably. This concordance of different observations, each probing different aspects of cosmic evolution, gives us confidence in the standard cosmological model while highlighting areas where our understanding remains incomplete. The cosmic microwave background radiation has proven to be one of our most powerful tools for understanding the universe's most mysterious components. Dark matter and dark energy. These invisible constituents, which together make up 95% of the universe's energy density, leave their fingerprints on the patterns of the cosmic microwave background in subtle but measurable ways. Through careful analysis of these ancient photons, we've gained insights into the nature and behavior of dark matter and dark energy that would be impossible to obtain through other observations alone. Dark matter's influence on the cosmic microwave background begins long before recombination. Unlike ordinary matter, which was tightly coupled to radiation in the early universe, dark matter interacted only through gravity. This meant that dark matter could begin clustering under its own gravity much earlier than ordinary matter, creating gravitational potential wells that would later influence the distribution of baryons and photons. By the time of recombination, dark matter had already formed a complex web of structures, from small clumps to vast filaments, providing the gravitational scaffolding around which ordinary matter would later accumulate. The acoustic oscillations in the cosmic microwave background provide a precise measure of the dark matter density. While baryons participated directly in these oscillations, compressed by gravity and bouncing back due to radiation pressure, dark matter provided additional gravity without contributing to the pressure. This altered the dynamics of the oscillations in measurable ways. The depth of the gravitational potential wells, the speed of sound in the baryon photon fluid, and the damping of oscillations on small scales all depend on the ratio of dark matter to ordinary matter. The third acoustic peak in the cosmic microwave background power spectrum is particularly sensitive to the dark matter density. This peak corresponds to a mode that was inside the sound horizon at recombination, meaning it had time to undergo compression and rarefaction. The height of this peak relative to the first peak depends strongly on the amount of dark matter present. Measurements show that dark matter outweighs ordinary matter by a factor of about 5.4, a ratio determined with precision better than 2%. The cosmic microwave background also constrains the properties of dark matter particles themselves. If dark matter particles were moving at relativistic speeds in the early universe, they would have streamed out of small-scale potential wells, suppressing structure formation on those scales. This would appear as a suppression of cosmic microwave background fluctuations at high multipoles. The absence of such suppression tells us that dark matter was already non-relativistic, or cold, at the time of recombination, ruling out light particles like standard neutrinos as the primary component of dark matter. The possibility that dark matter might interact with itself or with radiation beyond gravity has been extensively tested using cosmic microwave background data. Self-interacting dark matter would alter the growth of structure in ways that would affect the cosmic microwave background through secondary effects, like gravitational lensing. Dark matter-photon interactions would directly affect the acoustic oscillations, changing the effective number of fluid components. Current limits from the cosmic microwave background constrain any such interactions to be extremely weak, billions of times weaker than electromagnetic interactions. The cosmic microwave background has also been used to search for dark matter annihilation or decay. If dark matter particles can annihilate or decay into standard model particles, this would inject energy into the primordial plasma, potentially affecting recombination and the cosmic microwave background. The precise agreement between observations and standard predictions limits the rate of such processes, providing constraints on dark matter models that complement direct detection experiments and particle collider searches. Dark energy's impact on the cosmic microwave background is more subtle than dark matter's, but no less important. The primary effect comes through the angular diameter distance to the surface of last scattering. Dark energy affects the expansion history of the universe, which determines how far light has travelled since recombination, and thus the angular size of features in the cosmic microwave background. The position of the acoustic peaks depends on this angular diameter distance, providing a measure of the dark energy density. The integrated Sachs-Wolf effect provides a more direct probe of dark energy. In a matter-dominated universe, gravitational potentials remain constant with time once structures stop growing. However, in a universe with dark energy, the accelerated expansion causes gravitational potentials to decay with time. Cosmic microwave background, photons travelling through these evolving potentials experience a net energy change, creating additional large-scale anisotropies. This effect has been detected by cross-correlating cosmic microwave background maps with galaxy surveys, providing independent evidence for dark energy. The late-time evolution of structure, influenced by dark energy, affects the cosmic microwave background through gravitational lensing. As cosmic microwave background photons travel through the universe, their paths are deflected by the gravitational fields of intervening matter. The strength of this lensing depends on the growth of structure, which is suppressed by dark energy. Measurements of cosmic microwave background lensing therefore constrain both the dark energy density and its equation of state. The equation of state of dark energy conventionally parameterized as the ratio of pressure to energy density and denoted W, determines how dark energy's density evolves with cosmic expansion. For a cosmological constant, W equals exactly -1, meaning the energy density remains constant as the universe expands. Alternative dark energy models predict different values or time evolution of W. The cosmic microwave background, particularly when combined with other observations, constrains W to be very close to -1, consistent with a cosmological constant but not excluding slowly varying dark energy models. The growth rate of cosmic structure provides another window into dark energy through cosmic microwave background observations. Dark energy opposes gravitational clustering, slowing the growth of structure at late times. This affects the amplitude of gravitational lensing of the cosmic microwave background and the magnitude of the integrated Sachs-Wolf effect. By measuring these effects at different angular scales which probe different epochs of cosmic history, we can trace how dark energy has influenced structure formation over billions of years. The cosmic microwave background has revealed an intriguing tension in measurements of the current expansion rate, known as the Hubble constants. Values derived from cosmic microwave background observations, which essentially measure the expansion rate in the early universe, and extrapolate forward using the standard cosmological model, yield a Hubble constant of about 67 kilometers per second per megaparsec. Direct measurements in the local universe using supernova and other distance indicators give values around 73 kilometers per second per megaparsec. This discrepancy, if not due to systematic errors, might indicate new physics beyond the standard model, possibly related to dark energy or dark matter. Early dark energy models have been proposed to resolve the Hubble tension. These models introduce a component that behaved like dark energy in the early universe, before the conventional dark energy dominated. Such early dark energy would affect the sound horizon at recombination, changing the interpretation of cosmic microwave background data in a way that could reconcile the different Hubble constant measurements. The cosmic microwave background data constrain such models, requiring any early dark energy to constitute less than about 5% of the universe's energy density at recombination. The possibility of dark energy clustering, rather than being perfectly smooth, has been investigated using cosmic microwave background data. If dark energy can cluster gravitationally, it would affect structure formation and create additional contributions to the integrated Sachs-Wolf effect. Current observations are consistent with smooth dark energy, placing stringent limits on any clustering. These constraints help distinguish between different theoretical models of dark energy, such as quintessence fields, versus modifications to general relativity. Interactions between dark energy and dark matter, sometimes called coupled dark energy models, predict distinctive signatures in the cosmic microwave background. Such interactions would alter the growth of structure and change the evolution of the universe's expansion rate in ways that would affect both primary and secondary cosmic microwave background anisotropies. The precise agreement between observations and standard model predictions limits any such coupling to be extremely weak, less than a few % of gravitational strength. The cosmic microwave background has been used to test whether dark energy might actually be a modification of gravity rather than a new form of energy. Modified gravity theories, such as FR gravity or scalar tensor theories, predict different relationships between the expansion rate and the growth of structure than standard general relativity with dark energy. The combination of cosmic microwave background measurements with galaxy surveys and weak lensing observations provide stringent tests of these theories, so far finding no significant deviations from general relativity. The stability of dark energy over cosmic time is another question addressed by cosmic microwave background observations. If dark energy's properties varied significantly with time, this would affect the distance to the surface of last scattering and the growth of structure in ways that would be imprinted on the cosmic microwave background. Current data limit any variation in the dark energy equation of state to less than about 10% since recombination, suggesting remarkable stability over billions of years. Phantom dark energy models, where W is less than -1, predict that the universe will end in a big rip as dark energy's density grows without bound. The cosmic microwave background constrains such models by limiting how negative W can be. Current observations require W to be greater than about -1.1, ruling out big rip scenarios in the near future, but not excluding them entirely. The cosmic microwave background has also been used to search for evidence of extra dimensions, which appear in some theories attempting to explain dark energy. Large extra dimensions would affect the expansion rate of the universe and the growth of structure in ways that would be visible in cosmic microwave background data. The absence of such signatures places limits on the size of any extra dimensions and the energy scale at which gravity might deviate from four-dimensional behavior. Anthropic arguments about dark energy have been informed by cosmic microwave background observations. The observed value of dark energy is surprisingly small compared to theoretical expectations, the famous cosmological constant problem. Some physicists argue that if dark energy were much larger, structures couldn't form and observers like us couldn't exist. The cosmic microwave background's precise measurements of cosmological parameters help quantify these anthropic arguments and explore whether our universe's properties are typical or exceptional. The future of dark matter and dark energy studies with the cosmic microwave background looks promising. Next-generation experiments will measure polarization with unprecedented precision, potentially detecting primordial gravitational waves that would constrain inflation models connected to dark energy. Improved measurements of gravitational lensing will better map the dark matter distribution and test dark energy models. The combination of cosmic microwave background data with upcoming large galaxy surveys will provide even tighter constraints on the nature of these mysterious components. The cosmic microwave background has revealed that we live in a universe dominated by components we don't understand. Dark matter, 5 times more abundant than ordinary matter, forms the gravitational backbone of cosmic structure, but remains undetected in laboratory experiments. Dark energy, making up nearly 70% of the universe, drives accelerated expansion through a mechanism that challenges our understanding of fundamental physics. Yet through the ancient light of the cosmic microwave background, we can measure these mysterious components with percent-level precision, a remarkable achievement that would have seemed impossible just decades ago. The future of cosmic microwave background research stands at an exciting threshold, with new technologies and observational strategies poised to unlock secrets that have remained hidden in this ancient light. Next-generation experiments, both ground-based and space-based, promise to push our measurements to fundamental limits set by physics itself. These future observations will address some of the most profound questions in cosmology. Did cosmic inflation really occur? What is the nature of dark matter and dark energy? Are there signatures of physics beyond our standard models? The answers may fundamentally reshape our understanding of the universe. The search for primordial B-mode polarization remains one of the highest priorities in cosmology. These faint swirling patterns in the cosmic microwave background polarization, if detected, would provide direct evidence for gravitational waves from cosmic inflation. The amplitude of these signals depends on the energy scale of inflation, with detection implying that inflation occurred at energies approaching the grand unification scale, about 10 to the 16 GeV. This would represent our first observational window into physics at energy scales far beyond what any particle accelerator could achieve. Current and planned experiments are pushing toward the sensitivity needed to detect or rule out primordial B modes at increasingly small amplitudes. The Simons Observatory, currently under construction in the Atacama Desert, will deploy over 60,000 detectors observing at multiple frequencies. This massive increase in detector count, combined with exquisite control of systematic errors, will allow measurements of the tensor to scalar ratio down to about 0.003, an order of magnitude better than current limits. CMB-S4, a next-generation ground-based experiment planned for the end of this decade, will employ over 500,000 detectors distributed across multiple telescopes in Chile and at the South Pole. This ambitious project, involving most of the cosmic microwave background community, aims to achieve the sensitivity needed to detect primordial B modes if the tensor to scalar ratio is above 0.001. At this level, we would be probing inflation models that make specific predictions about the fundamental physics of the early universe. Space-based missions offer unique advantages for cosmic microwave background observations, avoiding atmospheric emission and providing access to the full sky. LightBird, a Japanese-led satellite mission planned for launch in the late 2020s, will map the entire sky in 15 frequency bands, focusing on large-scale B-mode polarization. The European Space Agency is studying similar concepts, recognizing that definitive measurements of primordial gravitational waves may require observations from space. The challenge of foreground removal becomes increasingly critical as we push to detect fainter signals. Galactic dust emission, synchrotron radiation from cosmic ray electrons, and other astrophysical sources can mimic or obscure the cosmological signals we seek. Future experiments will observe at many frequencies to separate these components based on their different spectral signatures. Machine learning algorithms are being developed to identify and remove foregrounds with unprecedented accuracy, though the ultimate limit may be set by our understanding of the foregrounds themselves rather than instrumental sensitivity. Beyond the search for primordial gravitational waves, future cosmic microwave background observations will address numerous other fundamental questions. The effective number of relativistic species in the early universe, conventionally expressed as the effective number of neutrino species, could reveal the existence of new particles beyond the standard model. Precision measurements of the cosmic microwave background damping tail, the suppression of power on small angular scales, can constrain this parameter to a precision of about 1%, potentially detecting deviations from the standard value of 3.044. The sum of neutrino masses, one of the few particle physics parameters not measured in laboratory experiments, will be determined by future cosmic microwave background observations combined with large-scale structure surveys. Massive neutrinos suppress the growth of structure on scales smaller than their free-streaming length, affecting both the gravitational lensing of the cosmic microwave background and the matter power spectrum. Next-generation experiments aim to measure the sum of neutrino masses with a precision of about 20 millielectron volts, sufficient to determine the neutrino mass hierarchy. Cosmic birefringence, a rotation of the polarization plane of cosmic microwave background photons as they travel through space could signal new physics beyond the standard model. Such rotation could be caused by pseudoscalar fields, like the axion proposed to solve the strong CP problem in particle physics, or by violations of fundamental symmetries. Current limits on cosmic birefringence are at the degree level, but future experiments will push these limits down by orders of magnitude. The search for primordial non-Gaussianity continues to be a major focus of cosmic microwave background research. While inflation generically predicts nearly Gaussian fluctuations, different models predict different levels and types of non-Gaussianity. Detection of significant non-Gaussianity would rule out simple single-field inflation models and could provide evidence for multiple fields during inflation, non-standard kinetic terms, or alternatives to inflation altogether. Future experiments will constrain the non-Gaussianity parameter FNL to levels below 1, approaching the predictions of the simplest inflation models. Spectral distortions of the cosmic microwave background from a perfect blackbody spectrum encode information about energy injection in the early universe. Processes like silk damping, where acoustic oscillations on small scales convert to heat, create characteristic distortion patterns. Future missions like PIXIA, Primordial Inflation Explorer, or similar concepts could detect these distortions, providing a window into the universe between the end of nuclear synthesis and recombination, an epoch currently inaccessible to direct observation. The cosmic microwave background may also carry signatures of phase transitions in the early universe. If the universe underwent first-order phase transitions, perhaps associated with grand unification or supersymmetry breaking, these could have created topological defects, like cosmic strings or domain walls. Such defects would leave distinctive patterns in the cosmic microwave background, including step-like discontinuities from cosmic strings or characteristic patterns from texture unwinding. The non-detection of such signatures already constrains these models, and future observations will provide even tighter limits or potential discoveries. Rayleigh scattering features in the cosmic microwave background spectrum, caused by scattering off neutral hydrogen and helium during recombination, provide a direct probe of the recombination process itself. These features, predicted to be at the level of a few hundred nanokelvin, are beyond current sensitivity but might be detectable with future technology. Their detection would provide a new window into the physics of recombination and could reveal unexpected processes in the early universe. The patchy screening effect, where different lines of sight experience different optical depths during rionization, creates additional fluctuations in the cosmic microwave background. These fluctuations, particularly in polarization, encode information about the topology and timeline of rionization. Future high-resolution observations could map the reionization process in 3 dimensions, revealing how the first stars and galaxies transform the universe from neutral to ionized. Moving lens effects, where the time variation of gravitational potentials due to peculiar velocities of massive structures affects cosmic microwave background photons, represent another frontier for future observations. These effects are predicted to be extremely small at the sub-microkelvin level, but could provide unique information about the growth of structure and tests of general relativity on cosmological scales. The possibility of detecting the cosmic neutrino background indirectly through its effect on the cosmic microwave background represents an exciting future prospect. While direct detection of these relic neutrinos remains beyond current technology, their gravitational influence on the cosmic microwave background and large-scale structure might be measurable with next-generation experiments. This would provide our first observational access to the universe when it was less than 1 second old. Anomalies in current cosmic microwave background data continue to puzzle cosmologists and may hint at new physics. The hemispherical power asymmetry, where one hemisphere of the sky shows slightly more power than the other, remains unexplained. The alignment of low multipole moments, sometimes called the axis of evil, seems to define a preferred direction in the universe. The cold spot in the southern hemisphere appears too large and too cold to be a typical fluctuation. Future observations with better sensitivity and frequency coverage will determine whether these anomalies are statistical flukes, systematic errors, or signs of new physics. The combination of cosmic microwave background observations with other cosmological probes will be crucial for future progress. Cross-correlation with galaxy surveys will map the growth of structure with unprecedented precision. Combining cosmic microwave background lensing with galaxy-weak lensing will provide precise measurements of the matter distribution. Joint analysis with gravitational wave observations could reveal the equation of state of dark energy and test general relativity on cosmological scales. Technological advances continue to push the boundaries of what's possible. Quantum sensors might achieve sensitivity beyond classical limits. Metamaterial optics could provide better control of systematic errors. Advanced cryogenic systems could cool detectors to temperatures where thermal noise becomes negligible. Machine learning algorithms could extract information from the data that traditional analysis methods miss. The ultimate limits of cosmic microwave background observations are set by fundamental physics. Gravitational lensing creates an irreducible confusion that limits our ability to measure primordial signals on small scales. The finite number of modes available in our observable universe creates cosmic variance, a fundamental statistical uncertainty. Despite these limits, there remains enormous discovery potential in the cosmic microwave background. With each improvement in sensitivity and each new observable potentially revealing unexpected aspects of our universe. The cosmic microwave background radiation invites us to contemplate questions that transcend the boundaries of physics and astronomy, touching on philosophy, existence, and our place in the cosmos. This ancient light, carrying information from when the universe was less than 400,000 years old, connects us directly to the origins of everything we know. It transforms abstract cosmological concepts into measurable quantities, yet in doing so, it raises profound questions about the nature of reality, the limits of knowledge, and the meaning of existence in a universe that began in a hot, dense state 13.8 billion years ago. The discovery that we can literally see the afterglow of the Big Bang forces us to confront the reality of cosmic evolution. The universe has not always existed in its current form, but has undergone dramatic transformations from a hot, dense, nearly uniform state to the cold, sparse, highly structured cosmos we inhabit today. This evolution, from simplicity to complexity, from uniformity to diversity, mirrors patterns we see throughout nature, from the development of biological organisms to the emergence of consciousness itself. The notion that the universe had a beginning raises immediate questions about what, if anything, came before. The standard Big Bang model, informed by cosmic microwave background observations, traces the universe back to a singularity where our physical theories break down. Inflation pushes this problem back, but doesn't eliminate it entirely. The cosmic microwave background shows us the universe at a very early time, but it cannot tell us about the ultimate origin or whether the concept of before the Big Bang even has meaning. The uniformity of the cosmic microwave background across the sky presents us with a remarkable fact. Regions of the universe that have never been in causal contact show nearly identical properties. This horizon problem, largely resolved by inflation, suggests that the entire observable universe shares a common origin smaller than an atomic nucleus. Every particle in our bodies, every atom in Earth, every star we see in the night sky emerged from this primordial seed, making us all, in the most literal sense, cosmic relatives. The tiny fluctuations in the cosmic microwave background, those 1 part in 100,000 variations, humble us with their implications. These minute density differences, possibly originating from quantum fluctuations during inflation, eventually grew into galaxies, stars, planets, and ultimately life itself. Our existence depends on these incredibly small imperfections in the early universe. Had the universe been perfectly uniform, structure would never have formed, and we would not be here to observe it. The precision with which we can measure the cosmic microwave background reveals both the power and limitations of human knowledge. We can determine the age of the universe to within 21 million years, measure its composition to percent-level accuracy, and map its geometry with exquisite precision. Yet this same precision highlights what we don't know: the nature of dark matter and dark energy, the physics of the very early universe, and whether our observable universe is all that exists. The cosmic microwave background confronts us with the concept of cosmic loneliness. The same observations that reveal the universe's history also show its vastness and emptiness. The average density of matter in the universe is about 6 hydrogen atoms per cubic meter, and this density continues to decrease as the universe expands. The cosmic microwave background itself, once a brilliant glow filling all of space, has cooled to a whisper barely above absolute zero and will continue cooling forever as the universe expands. The anthropic principle finds compelling expression in cosmic microwave background observations. The precise values of cosmological parameters measured from this ancient light appear fine-tuned for the existence of complexity and life. If the density of dark energy were slightly larger, galaxies would never have formed. If the amplitude of primordial fluctuations were much different, the universe would either be a uniform gas or would have collapsed into black holes long ago. Whether this apparent fine-tuning reflects necessity, chance, or selection effects in a multiverse remains one of the deepest questions in cosmology. The discovery of dark matter and dark energy through cosmic microwave background observations reminds us of the limits of human perception and intuition. 95% of the universe consists of components that don't interact with light and which we've never directly detected. Our everyday experience, evolved for survival on Earth's surface, provides no preparation for understanding a universe dominated by invisible components. The cosmic microwave background forces us to accept realities far removed from common sense. The cosmic microwave background also raises questions about the nature of scientific knowledge itself. Our interpretation of this ancient light relies on long chains of theoretical reasoning, from quantum mechanics and general relativity to thermodynamics and nuclear physics. We assume that physical laws measured in Earth laboratories apply throughout the universe and across cosmic time. The success of these assumptions in explaining observations gives us confidence, but we cannot escape the fact that we're extrapolating far beyond direct experience. The concept of the observable universe, clearly defined by cosmic microwave background observations, introduces profound limitations to knowledge. We can only see regions from which light has had time to reach us since the Big Bang. Beyond our cosmic horizon lie regions forever hidden from our view, possibly infinite in extent. The cosmic microwave background shows us the boundary of the observable, but cannot tell us what lies beyond. We must accept that there are questions about the universe that may be unanswerable in principle, not just in practice. The arrow of time finds clear expression in the cosmic microwave background. The second law of thermodynamics tells us that entropy increases with time, and the cosmic microwave background represents a state of very low entropy compared to today's universe. This ancient light thus defines a direction in time, from the smooth early universe to the clumpy present, from low entropy to high. Yet the fundamental laws of physics are largely time-symmetric, leaving the origin of time's arrow as one of physics' great mysteries. The cosmic microwave background connects us to the concept of cosmic memory. These ancient photons carry information about the state of the universe billions of years ago, a kind of cosmic memory preserved in radiation. Every observation of the cosmic microwave background is an act of cosmic archaeology, uncovering information about events that occurred when the universe was young. This light is the universe's autobiography, written in a language of temperature fluctuations and polarization patterns. The role of consciousness in a universe revealed by the cosmic microwave background presents intriguing questions. We are arrangements of atoms that emerged from the Big Bang, evolved through billions of years of cosmic and biological evolution, and developed the capacity to observe and understand our origins. The universe has, in a sense, developed the ability to observe itself through conscious beings like us. Whether consciousness is an accidental byproduct of cosmic evolution or plays some more fundamental role remains an open question. The future implied by cosmic microwave background observations is sobering. The discovery of dark energy suggests that the universe will expand forever, growing ever colder and more dilute. The cosmic microwave background will continue cooling, eventually becoming undetectable. Stars will cease forming, black holes will evaporate, and the universe will approach a state of maximum entropy. This heat-death scenario, trillions of years in the future, represents the ultimate fate implied by our current understanding. Yet the cosmic microwave background also tells a story of remarkable creativity and emergence. From near uniformity emerged complexity. From a hot plasma emerged atoms, stars, galaxies, and life. The same physical processes that will eventually lead to heat death first created conditions allowing for biology, consciousness, and meaning. The cosmic microwave background reminds us that we exist in a special epoch when the universe is neither too young nor too old for complexity and life. The philosophical implications of inflation, strongly supported by cosmic microwave background observations, are profound. If inflation is correct, our observable universe emerged from a region smaller than a proton, expanded by factors of trillions upon trillions in a fraction of a second. This suggests that universe creation might be a natural process, possibly occurring repeatedly. The cosmic microwave background might be showing us just one bubble in an infinite multiverse, each bubble with potentially different physical high laws. The measurement of the cosmic microwave background represents a triumph of human reason and curiosity. That beings on a small planet orbiting an ordinary star can detect and interpret radiation from the early universe, determining the age, composition, and fate of the cosmos, seems almost miraculous. The cosmic microwave background reminds us that despite our cosmic insignificance, in terms of size and duration, we possess the remarkable ability to comprehend the universe that created us. As we reach the end of our journey through the story of the cosmic microwave background, we find ourselves not at a conclusion, but at a threshold of understanding. This ancient light, this whisper from the beginning of time, has revealed to us the grand narrative of cosmic evolution, while simultaneously deepening the mysteries we seek to solve. The cosmic microwave background stands as humanity's greatest archaeological discovery, not of civilizations past, but of the universe itself, frozen in time at the moment when atoms first formed and light could finally travel freely through space. Throughout this exploration, we've seen how two radio engineers in New Jersey, simply trying to eliminate noise from their antenna, stumbled upon the echo of creation itself. We've traced the journey of photons that have travelled for 13.8 billion years, carrying with them information about the universe when it was only 380,000 years old. We've examined how tiny quantum fluctuations, stretched to cosmic scales by inflation, became the seeds for all the structure we see in the universe today, from the smallest galaxies to the vastest cosmic voids. The cosmic microwave background has transformed cosmology from a field of speculation into a precision science. Through careful observation of this ancient light, we now know the age of the universe to within 21 million years, a precision that would have seemed impossible just decades ago. We've measured the composition of the universe, finding that ordinary matter makes up less than 5% of its content, while mysterious dark matter and even more enigmatic dark energy dominate the cosmic inventory. We've determined that space itself is flat to within observational uncertainty, confirming predictions from inflationary theory. Yet for all these triumphs, the cosmic microwave background also humbles us with what it reveals about our ignorance. Dark matter, making up 27% of the universe, remains unidentified despite decades of searches. Dark energy, comprising 68% of the universe and driving its accelerated expansion, defies theoretical understanding. The physics of inflation, if it occurred, operated at energies far beyond what we can probe in any laboratory. The cosmic microwave background shows us how much we've learned while simultaneously revealing how much more there is to discover. The technological achievements that enable cosmic microwave background observations represent some of humanity's most impressive accomplishments. We've built detectors that operate within millikelvins of absolute zero, sensitive to temperature changes of a few millionths of a degree. We've launched satellites that map the entire sky with arc-minute precision, positioned at Lagrange points millions of kilometers from Earth. We've developed analysis techniques that can extract cosmological information from maps containing billions of data points, separating primordial signals from numerous sources of contamination. Looking forward, the future of cosmic microwave background research promises even more remarkable discoveries. Next-generation experiments will search for the signature of primordial gravitational waves, potentially opening a window to the universe when it was only 10 to the negative 35 seconds old. Improved measurements of neutrino masses, dark energy evolution, and primordial non-Gaussianity will test our fundamental theories of physics. The combination of cosmic microwave background data with observations from gravitational wave detectors, galaxy surveys, and other cosmological probes will provide an increasingly complete picture of cosmic evolution. The cosmic microwave background also connects us to profound questions about existence itself. Every atom in our bodies, except for hydrogen, was forged in the nuclear furnaces of stars. But the hydrogen itself, the protons and electrons that make up the simplest and most abundant element, formed in the first minutes after the Big Bang. The patterns we see in the cosmic microwave background determined where galaxies would form, including the galaxy that hosts our solar system. In a very real sense, we can see our origins written in the patterns of this ancient light. As we contemplate these connections between the cosmic and the personal, between ancient light and present existence, we're reminded of the remarkable fact that the universe has evolved the capacity to understand itself. Through billions of years of cosmic evolution, from the first atoms to the first stars, from simple molecules to complex life, from early organisms to conscious beings, the universe has developed the ability to observe, measure, and comprehend its own history. We are the universe becoming aware of itself, using tools like cosmic microwave background observations to read our own cosmic story. The story of the cosmic microwave background is far from complete. New technologies, new theoretical insights, and new observations continue to reveal previously hidden aspects of this ancient light. Young scientists entering the field today will have opportunities to make discoveries that we can barely imagine. Perhaps they will detect primordial gravitational waves, revealing the physics of inflation. Perhaps they will find evidence for physics beyond our standard models, opening new realms of understanding. Perhaps they will discover something completely unexpected, as surprising as Penzias and Wilson's accidental discovery was in 1964. For those inspired by this cosmic story, there are many ways to participate in the ongoing adventure of discovery. Professional scientists continue to push the boundaries of observation and theory, but citizen scientists also contribute through projects that classify galaxies, search for patterns in data, and help process the enormous datasets generated by modern surveys. Students at all levels can engage with cosmology through courses, online resources, and public lectures. Anyone with curiosity about the universe can follow developments through science journalism, documentaries, and popular books. The cosmic microwave background reminds us that we live in a remarkable epoch of cosmic history. We exist at a time when the universe is old enough for complex structures and life to have evolved, yet young enough that we can still see evidence of its beginning. The cosmic microwave background is still detectable, though it continues to cool and fade as the universe expands. Future civilizations, trillions of years from now, will live in a universe where this ancient light has faded beyond detectability, where evidence of the Big Bang has been erased by cosmic expansion. This places a special responsibility on our generation and those that follow. We are among the first civilizations in cosmic history capable of detecting and understanding the cosmic microwave background, and we may be among the last who can observe it before it fades forever. The knowledge we gain, the records we keep, and the understanding we develop may be the only preserved memory of the universe's beginning for all future time. As we prepare to rest, to let sleep carry us away from conscious thought, we might reflect on the profound connections revealed by the cosmic microwave background. The same physical processes that created the patterns in this ancient light also led, through billions of years of evolution, to our existence. We are not separate from the cosmos, but an integral part of its ongoing story. The atoms in our bodies, the energy that powers our thoughts, the very space we occupy, all emerge from the same primordial event, whose echo we detect in the cosmic microwave background. The cosmic microwave background teaches us patience and perspective. Its photons travelled for billions of years before reaching our detectors, a journey that makes our human timescales seem infinitesimal. Yet it also teaches us that small things can have enormous consequences, that quantum fluctuations can become galaxy clusters, that patient observation can reveal profound truths. It reminds us that we are part of something immeasurably vast and ancient, yet also that our capacity to understand and appreciate this cosmos makes us special. In the gentle static of an untuned radio, in the soft hiss that Penzias and Wilson first heard, lies the echo of everything that has ever existed. This cosmic microwave background, this afterglow of creation, connects us to the beginning of time, to the edges of space, and to the fundamental processes that govern reality. It tells us that we live in a universe with a history, a present and a future, a universe that evolved from simplicity to complexity, from darkness to light, from unconscious matter to conscious observers capable of wonder. As you drift off to sleep tonight, perhaps you'll think about those ancient photons still arriving at Earth after their 13.8 billion year journey. They've travelled through the vast emptiness of space, past galaxies being born and dying, through the cosmic web of dark matter, carrying their message from the early universe to us. In detecting and understanding these photons, we've read a page from the universe's autobiography, written in the faint glow of ancient light. If this journey through the cosmic microwave background has sparked your curiosity, if you found wonder in the story of ancient light and cosmic evolution, consider subscribing to continue exploring the mysteries of our universe. Like and share this story with others who might find inspiration in understanding our cosmic origins. Together, we can continue to unravel the mysteries written in the cosmic microwave background, that ancient light that connects us all to the very beginning of everything.